Welcome to this extended version of my lightning talk given this year at the JuliaCon 2022. I want to give a little bit more detail than in 8 minutes about Manopt.jl and optimization on Riemannian manifolds. In optimization in general, we are concerned with finding some x where f is minimized. So we're looking for a minimizer of a function f. For example, numerically in packages like jump. Challenges are here if you don't want to consider the whole space Rm, but just over here some set C where you're constrained to, for example, the set of unit vectors. Or if you have certain symmetries or invariances in your function f that render your optimization problem more challenging. For example, you might have a situation where certain rotations of your problem yield a constant function value independent of where you are. So wherever you are, a rotation doesn't change your function value. Then you have an invariance with respect to that rotation, and that might make your optimization problem more complicated in general. And one way to solve this is geometric optimization or optimization on Riemannian manifolds, where you rephrase the problem to be defined on a Riemannian manifold, maybe just by restricting to the set C, if it's unit vectors, for example, the sphere. And the one advantage that directly appears is, compared to the constraint problem being on the unit vectors, so constrained to unit vectors, on a Riemannian manifold like the sphere, this directly becomes an unconstrained problem again. So we can just tackle that with optimization, with solvers that are tailored towards unconstrained optimization, like a gradient descent. And that's what I want to investigate and talk about, how to do that in Julia. So what's a Riemannian manifold M? At first glance, it is a set that is covered with a suitable collection of charts, so that subsets of this manifold are identified with open subsets of Rd. So locally, a manifold looks like a d-dimensional space. For example, if you're in the sphere, it locally looks like R2, the surface of the Earth, for example. And another thing that we need is, at every point, we have a tangent space. For the sphere, that would just be the tangent plane, with an inner product that's continuously varying. But at every point, we have a tangent space, kind of like of directions that curves can run through this point. That's the tangent space. To make that a little bit more formal, a d-dimensional Riemannian manifold has the following things. The tangent space we already had on the last slide. The geodesic connecting P and Q is the shortest curve connecting both. The inner product will be denoted by just round brackets and the index P at the end. And then we have two very important ingredients. That's the logarithmic map and the exponential map. If we have some point P and a starting direction X, then we can phrase finding the corresponding geodesic starting into that direction as an ordinary differential equation. So that would be the ordinary differential equation that yields a shorted geodesic, or one that doesn't provide any acceleration with respect to the given inner product, where that starts at P in direction X. That's exactly what we have here for the exponential map. This ODE, if we solve that and evaluate the corresponding curve at 1, we reach some point which is called the exponential map. First comparison to Euclidean space. In Euclidean space, this would just be P plus X. And the inverse question is, if I have a point Q, what's the direction I have to walk into to get there? That's the logarithmic map. Those are two very important ingredients. But you already see it's more complicated than just computing plus, because we have to solve maybe an ODE if we don't have a closed form solution. And the last thing I want to mention here is parallel transport. Since the tangent space is different for for example, for the sphere, it's different tangent planes to the sphere. We need something like parallel transport, which can again be phrased as an ODE to solve, which moves a tangent vector y here from P along the geodesic over to Q. So that's the parallel transport from P to Q of our tangent vector y given in the image on the right. That's the terms that we need. I will always try to relate them to things either in Euclidean space or to the sphere during the talk. The parallel transport in the Euclidean space would just be the identity, because I want to have the same direction that's just parallel transported. That's where the name comes from. Okay, that's the terms we need on a Riemannian manifold. The first example is the sphere. So that's the set of unit vectors in d plus one dimensional space. Then we have the sphere as d. For example, S2 in R3 would be just the surface of the sphere. And then the tangent space is just all vectors that are orthogonal to the point P. Or if we compute P plus the tangent space, we really have the tangent plane to the sphere. And then, what I already said, the ODE we have to solve for the exponential map here has a nice closed form solution, because the shortest connection between 2 points on the sphere is just the connecting great arc. So we exactly just have to write down the formula for the great arc that starts in P in direction x. And this is the formula over here, how to compute that. And the parallel transport has also a nice closed form solution. So those are on the sphere really nice. But for the logarithmic map, or imagine in Rn that would just be minus, we already have a first problem, because it might not always be a function globally, because it doesn't have a unique answer in any case. So for example, if we have two opposing points, north and south pole on the sphere, then any vector that has the right length, so that we run half around the sphere, is a solution to this log question, how do I get to Q? So then it's not globally a map. I have to exclude the opposing points to make log actually a function that returns a tangent vector. So that's already one challenge we have, but on the sphere, luckily, as soon as they are not opposing, I also have a closed form formula that can be implemented easily. The second example are the Stiefel and the Grassmann manifold. The Stiefel manifold is all orthogonal bases for k-dimensional subspaces of Rn. So again, imagine you have R3, our room that we live in, and at k be 2, then we would look for two orthonormal vectors that span some subspace. For example, our slides here. So then this would be, for example, one orthonormal basis for the slides, R2 in R3. But for example, these two here would still, just the rotated version of both, describe the same subspace, just with another orthonormal basis. And these bases we write into a matrix. So here this would be P is in R3 times 2, because we want to describe a surface, a plane in R3. That would be the two orthonormal basis vectors in R3 that describe our plane, which is the slides. So that's the Stiefel manifold. We collect all these orthonormal bases, which is always k vectors in Rn, such that they are, well, unit length and pairwise orthogonal to each other. We already saw if I rotate such a basis, then I'm still in the same subspace if I rotate in the plane. So I have different ONBs to describe the same subspace. So if I have an optimization problem that is only concerned with finding the right subspace, then it's irrelevant which basis I take. So then we obtain the Grassmann manifold, which doesn't talk about the orthonormal basis, but the span of those, so just considers the subspace as an element of the manifold. Or in other words, all O and B's that describe one subspace, that is, I have, for example, two vectors and rotate them to describe the same subspace, then I'm still at the same point Q. I have different points on the Stiefel manifold, which are the same point on Grassmann, because I just consider their span. In other words, I can factor out anything that rotates the basis to leave the same subspace invariant. Or I have a quotient structure for the Grassmann manifold. So, for example, when I'm optimizing and looking for the best subspace to describe something, then the Grassmann manifold would be the right thing to phrase our optimization problem, and then use tools from Riemannian optimization. To implement a manifold, we have the package manifold base, which is just an interface or describes functions to implement a manifold. For example, the inner product that we already had, the Riemannian metric, the exponential and the logarithmic map. Or more general, since we have to solve an ODE for those, and that might be quite expensive, you can use a retraction, which is a first order approximation to the exponential map. And of course, the inverse retraction is then the same for the logarithmic map, where there might be different retraction methods M that you might want to use. The same way, we have parallel transport and vector transport too. Oh, there's a 2 missing here. Parallel transport 2 and vector transport 2, which does this parallel transport of the vector x from the tangent space at P to Q. And here the M mentioned everywhere is a subtype of the manifold, which is parametrized with this boldface F, which represents the field the manifold is over. So whether it's real valued vectors or matrices or something, we represent them with or complex or Hermitian ones. Exactly, quaternion ones. The next good thing is this interface also provides always a mutating version. So if you already have memory Q you want to work in place, then you can call X explanation mark. And all these are already used in manifold base to provide a few generic functions that are then automatically available. For example, the norm or the geodesic or the shortest geodesic, which are the two ones we had in the detection. P towards X and in direction X is geodesic, and if I provide 2 points, that use the shortest geodesic. You can still by dispatch re-implement them if you have something more efficient, but these are available as soon as you have the functions mentioned above, X and log, are enough to implement the geodesic. Based on that, Manifolds.jl is a library of manifolds, which provides a large set of libraries, but manifolds, but especially also different metrics for a manifold. You can take a different metric on the tangent spaces, Lie groups, and you can build more manifolds by building products or powers of manifolds. The tangent bundle TM is automatically available. You have a system to embed a manifold. The sphere S2 is embedded in R3. And we have a well-documented Documenter.jl-based homepage for that, where we also try to keep track of all mathematical formula as soon as there's a closed form solution. Examples, well, we already have the sphere in one example. Circle and torus are two matrices, manifolds that are available. Fixed rank matrices. We also had the example of Stiefel and Grassmann. You can change the inner product. Then you with generalized Stiefel and Grassmann, the hyperbolic space or rotations. Or for example, if you want to optimize over symmetric positive definite matrices, we got you covered. Or, which is used in physics quite a lot, the symplectic manifold or symplectic Stiefel manifold are also available. Besides the link, there's also a talk from JuliaCon 2020 about Manifolds.jl. Check that out for more details. Let's get back to optimization on manifolds. The goal of Manopt is to do this generically, so just to depend on manifold space, so that it works with any manifold. And then you have 3 ingredients to specify a solver for your optimization problem. So remember, we still want to solve argmin p from the manifold f of p. And then the problem contains everything that's static. The manifold that we work on, the cost function f that we want to consider, and further properties that we know of f. So maybe it's gradient, maybe it's Hessian, maybe it's proximal map, something like that. So that's the problem P. Furthermore, we need some options O, which is the dynamic data. And it might be, again, of a certain subtype of that. It stores, for example, the current iterate, maybe a stopping criterion for the algorithm. We will get into that in a minute. And any parameter you require to perform your iteration. So these together form then the complete plan to solve our optimization problem. And they can be used to implement both the initialize solver, kind of like to set everything up, and the step solver to perform the eth step. That's the 2 main things to implement for yourself if you want to solve an optimization problem. And then running the solvers, of course, you have to generate a specific problem, specific options, and call solve. Since this might be a little bit handcrafty, there's always a high-level interface. And as a first example, if we have our manifold M, our function f, the gradient, and some starting point p naught, then gradient descent with these parameters performs a gradient descent on that manifold with a reasonable default of all the other parameters involved. So it generates a gradient problem, mf grad f, with all the fixed static properties that we want to consider, and the gradient options, which will have to store the iterate and get initialized with p0 and a certain gradient, so they get initialized with the gradient grad f m p0. Okay, and then of course it runs the algorithm and returns the result using getSolverResult, which returns the current iterate stored in the specific options. Okay, things that are usually included is a stopping criterion, which is a functor itself. So as soon as you set it up, you get a functor that returns either true or false when you give it the problem, the current state of the options, and the current iterate. It has a default implementation to return a reason, but you can write that yourself if you want to provide a specific string why it returned true and says please stop. And the or and operators are overloaded to say I want to have a stopping criterion that says one of the two should be active, or both have to be active in order to stop the solver. So examples: stop after iteration n, stops after n iterations. And with the or, we say stop after n iterations, or when the gradient is less than 10 to the minus 8. So or when the gradient is small. And this is usually stored within the options. And for the gradient descent, stopping criterion is a keyword argument where you can override the reasonable default we provide, which is basically a certain n and a certain size of the gradient. The next thing that's usually included in the options, at least for gradient-based iterations, is step size and line search. So usually when we have the negative gradient direction to walk into, like this, then we still want to have a step size, how far we want to walk. And this might be a constant step size c, or for example, the Amio line search, which then doesn't search along a straight line, but for example, along geodesics on manifolds, or for example, the non-monotone line search. Again, these are stored within the options O, and one example would be to look along retractions for the line search, and the corresponding step size is then used to perform the actual step in the gradient method, for example. So this is actually a line from the gradient step, which then uses a certain retraction, not necessarily an exponential map, to be more efficient, and walks into that direction of the negative gradient with a certain step size. The next two things is how to print debug. So that is a decorator for the options. They get encapsulated in debug options. So O is our original options, and we make the D debug options. And then, well, there's a special dispatch for initialize step and solver step that does the original initialization or step and performs debug output. The same at the end when the stopping criterion returns true, then also a certain debug action is called DA that basically prints details you want to provide. And since the details are a little bit challenging, the easiest is that something like gradient descent has a debug equals keyword, which, for example, takes a symbol like iteration, which just prints the iteration number. Takes a debug action like debug cost, which just takes the options and prints the options in the problem and prints the current cost value. Can also be done by colon cost, but I wanted to demonstrate that debug cost is a debug action like mentioned above. And this is even the change of two values with a specific string giving the format you want to print. And colon stop gets stored in this in the end and prints the stopping reason after the end of the algorithm. So that's the easy way with the keyword for all the solvers to activate debug. And the same, maybe a little bit shorter, for recording values. So then we have a record action which collects values at every iteration instead of printing it, but it works the same way. So it's a decorator for the options. And also there's a record equals keyword for all the high-level interfaces like the gradient descent function, which then, well, you can set the return options to true to obtain the options and not the final iterate. And then you can easily access all recorded data that you wanted to have recorded during your solver run. Okay. In Manopt.jl, we implemented quite a few algorithms, for example, gradient descent that we already saw in one call. There's quasi-Newton available on Riemannian manifolds, especially a limited memory BFGS, but also nearly all other update rules, DFP, the Broyden class of update rules, a symmetric rank 1. Then there's, if you don't have a gradient, the meet or particle swarm. There's a subgradient method if your problem is non-smooth. There's, of course, just regions. And these three are, again, for the non-smooth optimization. So if your cost F is non-smooth, but has a certain additive form, Chambol POC, Douglas Washford, and cyclic proximal point. All of them require different things in the problem, but and then have specific options to work with that. But that's then exactly what you have to set up or use the high-level interface. But we are, of course, not the only ones. Besides the Julia package, Manopt.jl.org, there's Manopt.org, which is the first package written by Nicolas Baumol and colleagues in MATLAB. And there's PyManopt, written by Sebastian, Niklas, and James. PyManopt to work on manifolds in Python. Okay, let's get to an example. If we have the mean of n data points in R small n over here, then the mean would just be sum them all up and divide 1 by n. On a manifold, I cannot do that because there is no plus on a manifold. Just for the sphere, if I sum up all these points, it's not a unit vector anymore. And if I divide that by n, it's still not a unit vector. In just one case it is, and that's a boring case where all of them are the same. So this would be one scenario that we cannot do directly on a manifold, but we can rephrase this as an optimization problem. Turns out the mean is the minimizer, so the point minimizing the sum on the right, the sum of squared distances to all the data. And that is something we can write on a manifold because the distance is the length of the connecting shortest geodesic. Or a geodesic, if you have north and south pole, the distance is again well defined. The geodesic is not unique. And this is an optimization problem that we can write now on the manifold as well. So if we have points P1 to Pn on our manifold M, then the Riemannian centers of mass are given as minimizers of this function. And you already hear the first thing that's different. This minimizer is not necessarily unique. So it might be that the function is not convex, not globally convex, and that there's more than one minimizer to this function. It usually also doesn't have a closed form solution. But the nice thing is that if I look at one of these summands over here, so for example, a half distance squared to the ith data point, then I can specify the gradient. And with that, I can specify the gradient of my whole cost f that's given here. And hence I can use gradient descent to solve this, which would be one way to solve it. Let's look at that in code. If we have installed Manopt and Manifolds as packages in our Julia or APL, then just loading those two, and for completeness we also need linear algebra. We want to work on the sphere with n being 100 points. Then we can generate 100 points, which is just take a random point in R3 and normalize it to be a unit vector, and that's what we collect. Might not be the most reasonable case because we have quite uniformly distributed points in the sphere then, and the mean might not be unique. Locally, it might still be unique. But let's just take these 100 points. Then the cost function is just the distance from manifold space of pi to p squared and sum them up, where pi runs over the points that we generated, and p is the parameter of our cost function, which also takes the domain m as its first parameter. The gradient for that, Manopt provides grad distance, which again provides exactly the gradient that we wrote on the last slide, and this is then the computation we have to do to obtain the gradient of f, grad f. Then we can just call gradient descent, mf, the gradient, and let's say the first point as a starting point for the gradient descent. And this will work just fine. Alternatively, there's always the mutating variant. So if we already have memory for m, where we want to work in, for example, because we copied over the first point, then gradient descent exclamation mark performs an in-place gradient descent run in place of m without allocating more memory for points. Alternatively, this is how the cyclic proximal point looks like, where we have the prox distance, again given in Manopt.jl, and those are several separate functions. That way prox is a vector of functions, and the cyclic proximal points applies these step by step, and the lambda is a parameter that's modified. But then just calling cyclic proximal point with mf, this proxes and starting point, is another run of a solver that solves the same problem. And on some manifolds, this is more efficient than a gradient descent, but that's again depending on the manifold. Yeah, that's a few examples you can do by easily calling the high-level interfaces. And I can again could just add debug or record to these to print some details during the iterations or record certain values again during the iterations or at the end. Let's summarize. So Manopt.jl is a Julia package that first provides a framework to do optimization on arbitrary manifolds using manifold space. And it's also a library of optimization algorithms within this framework. That is, you get the generic step size and line search functions, you get debug and record capabilities, and have this generic stopping criterion mechanism to work with. There's also, you saw that for one cost function and for one gradient in the last example, there's a few cost functions, gradients, differentials, and proximal maps available and implemented to just make a few optimization tasks easier. And there's also a few tutorials at Manopt.jl.org to see how to work, for example, with a record. And finally, well, the next step that I want to attack is constraint optimization on manifolds. So a mix between my initial motivation and already being on a manifold, which is augmented Lagrangian method, the exact penalty method, or Frank-Wolfe on Riemannian manifolds, where the papers already exist, but there's no implementation in Julia available yet. And with that, here's a list of references. Most prominently, there's a paper in JOS, if you want to know a few more details about Manopt.jl. If you want to know more about the theory, there's the nice book by Ronny and Sepulchra on optimization on matrix manifolds, where the points on the manifold can be represented by matrices, which is also usually the case for every example that we had. The slides are online if you want to take a look at them in a nice format as a PDF like I presented here. And with that, thank you for your attention